Okay, before we learned valence bond theory. So from today, let's take a look at another theory called molecular orbital theory. It's the last part for chapter 10. Okay. So this is a different way of combining the atomic orbital to explain the covalent bonding. You know the molecules are composed of atoms, right? In other words, atoms are bonded together form molecules. So this molecular orbital theory is described as a covalent bond in terms of a molecular orbital that are combined by the atomic orbitals. Let's see details. Yeah. So this molecular orbital theory is different from the valence bond theory because it's consider all the atomic orbital of the bonding atoms involved, not just the valence electrons, like the valence bond theory. So let's take a look at it. So the basic idea for this molecular orbital theory is based on the wave characteristic of the electrons. You know, we learned in the chapter 7, so electromagnetic is kind of the wave. And also we learned electrons, also kind of waves. We also showed you how to calculate the wavelengths of the electrons based on their speed. So based on this idea, so for waves, there are some, I will show you in the next slide, there's some kind of phenomena called constructive interference. So in that case, for molecular orbital, we think it's a bonding molecular orbitals. And if the two waves are destructive, if they have that destructive interference, so they will form the antibonding molecular orbital. So what is constructive and destructive? I hope you have learned this one from your physics, but if not, it's okay. So this is a wave 1, and you see at certain times, as a function of time, the wave shows like that. Yeah, the magnitude is higher and lower, for example. And another wave have the same phase, which means at the same time, for example, this wave reach a maximum, another wave also reach a maximum. You see, in that case, we give them a name like in phase. Yeah. In other words, if you put them together, they overlap actually. So when these two waves with the in phase characteristic, when you're adding them together, the sum of the wave will be like this, which means their amplitude enhanced or increased, right? Because basically you're adding these two together. Yeah, this is a situation the two waves are in phase. If the two waves, like wave 1 and wave 2, like this, for example, the wave here go up, but another wave 2, they go down. They are opposite actually. When this go down, another one go up. So that two phase, we call them after phase. So what happens if we add in these two phases that have the after phase characteristics? So if you're adding them together, the sum of these two waves will be cancelled out to each other. Because this, for example, if this amplitude is 1, this amplitude is -1. So everywhere they cancel out. So basically you see nothing here. Yeah, so this is called constructive by this way, and this way is called destructive. Yeah, it's understandable, right? You see these two waves are destructed, and this one they constructed. Yeah. So this is a molecular orbital theory based on that wave idea. So according to this theory, the bonding molecular orbital are produced by adding atomic orbital together. So they are more stable when they are adding molecular orbital together. They are more stable than the atomic orbital that produced them. This is why they can form the molecular orbital, can form the bonds.
The bonding molecular orbital has greater electron density in the bond region.
You see, this is okay, I'll show you again.
The bonding molecular orbital has greater electron density in the bond region.
Yeah, the bonding molecular orbital, according to this theory, you have more electrons here because, it's adding together from atom 1 and atom 2, they adding together. So you have more electrons. You see, this is a little bit similar with the idea of the valence bond theory. Seems it's this shared electron, right? But it's another theory. So how about the anti-bonding orbital? Anti-bonding molecular orbitals are produced by subtracting atomic orbitals from each other. Just like the wave I showed you, the two waves are out of phase. They cancel out to each other. But here we see is subtract atomic orbital from each other. And there are less electrons between this nuclear. So they are less stable. That means you have higher energy, less stable than the atomic orbital that produce them.
The anti-bonding molecular orbital has reduced electron density in the internuclear region. The anti-bonding molecular orbital has reduced electron density in the internuclear region.
Yeah, if they have the reduced amount of electrons here, which means, the electrons interaction with the nuclear is less, right? Yeah. So this is not stable. Yeah, so it's called anti-bonding. Yeah, anti-bonding has higher energy. So this diagram can show the constructive bond is a bonding sigma molecular orbital is like this. This is a construct interaction will form this kind of bonding sigma molecular orbital. But on the other hand, for destructive interaction, they will form the anti-bonding sigma molecular orbital. You see less electrons in between the two atoms. So let's take hydrogen molecules as an example. We learned hydrogen atoms has 1 electrons and first filled in the 1s orbital, and another hydrogen atoms also have 1 electron filled into the 1s atomic orbital. Okay, this is the atomic orbital, these two. When they form the molecular orbital, MO, they form 1 bonding molecular orbital and anti-bonding molecular orbital. As we talked before, so the bonding has a lower orbital has a lower energy compared with their atomic orbital, but the anti-bonding orbital has a higher energy compared to the atomic orbital. So this is energetically not favorable. And so typically we use a star here to indicate this anti-bonding. This is sigma bond, but it's anti-bonding, sigma bond. So you have 2 electrons from the atoms, so that 2 electrons will fill in into the lower energy molecular bonding orbital. It will not go to here because the energy is higher, right? Yeah, you only have 2 electrons here. So this is a diagram for the formation of the hydrogen molecular orbital. So there are some rules for molecular orbital. Again, let's first read through these rules, and then I will show you how to use that rules. So the number for molecular orbital is always equal to the number for atomic orbital combined. For example, here you have 1 and 2 atomic orbital. Then the molecular orbital, you also have 2, 1, 2. The number are the same. Yeah. Secondly, fill the molecular orbital from the lower to higher energy. Yeah, this is why we filled this electron in the lower energy orbital, molecular orbital. We did not start from there. Yeah, in nature, it's always like this. Lower energy, yeah, preferred. Each molecular orbital can accommodate a maximum of 2 electrons with opposite spin. So this is the Pauling exclusion principle also applied here. You know, when we do the off-bar, the built-in principle in the chapter 7, when filled electrons into the atomic orbital, we use this principle. But here, this principle also works. The next one is when electrons are added to molecular orbital of the same energy, each orbital get 1 electron before any orbital get the second electron. This is exactly like the off-bar principle of the atomic orbital, right? Called Honda rules. I will show you how to say. Yes, I don't have a good example, but I will. Yeah, for example, if you have 1 orbital here and 1 orbital here, 2 orbital here. If you only have 2 electrons, you should put 1 electron here, 1 electron here. You should not put 2 electrons on 1 orbital, but leave another orbital empty. This is what this Honda rule said. You can check our chapter 7 lecture notes. So the last one is the total number of electrons in the molecular orbital is equal to the sum of all the electrons on the bonding atoms. Okay, what does that mean? So that means, for example, if you have 4 electrons here on the atomic orbital, 2 plus 2 is 4. You must have 4 electrons here too. Yeah. So you cannot put 3 here because you have 4 electrons. When they form the molecular orbital, the 4 electrons should be filled in. Otherwise, you lose some electrons, right? Yeah. Similarly, like here, if you have 1 electron from 2 atoms, so you will fill 2 electrons here. Yeah, you cannot fill 3, or you cannot only end up with 1 electron here. Because you have 2, you have to put 2. Yeah. So this is another example of the molecular orbital from the lithium molecules. This diagram shows, for example, here, a constructive interaction form the bonding sigma molecular orbital. So this is sigma 1s, this 1s, and this 1s. They form the sigma 1s molecular orbital, and when they are destructive, so they form the anti-bonding sigma molecular orbital. Like I said, we put a star here to indicate that is anti-bonding. You see how higher energy. So these 2 molecular orbitals are formed by 1s atomic orbital. How about the 2s atomic orbitals? They form the sigma 2s molecular orbitals. Yeah, one's bonding, one's anti-bonding with star. So 2 electrons filled into here. Yeah. So here you have you see you have more electrons sitting between, but this destructive have less electrons there. It's higher energy, less stable, like we discussed before. So it's also possible that possible interaction between the 2 equivalent p orbital. And before we talk about the like the s orbital. Let's take a look at the p orbital. So p, before we learned the p orbital can form either the pi bond and the sigma bond. If you forget, you can recall the sigma bond means the end-to-end or head-to-head interaction. It's stronger, like head-to-head. And the pi bond is shoulder-to-shoulder, like people stand up, shoulder-to-shoulder. If you draw it like this, it's like pi. This we learned before. This is like 2 people lying down, Yeah. And so in this case, so when the pi and the pi have the constructive interaction, they will form the bonding pi molecular orbital. Yeah. So you have the bigger electron density between these 2 atoms. For anti-bonding, similarly, you have less electron sitting between these 2 atoms. So this is called anti-bonding pi molecular orbital. Yeah, so sigma bonding here is similar with the s orbital. For example, p orbital can form the constructive interaction head-to-head, and then they have a bigger overlap here, more electrons sitting between. So this is called bonding sigma molecular orbital. And when they have the destructive interaction, so they form the anti-bonding sigma molecular orbital. You see here the electrons reduced. So the energy is higher, it's less stable. So the 2 possible interaction between the 2 equivalent p orbital. Yeah, not like s orbital. P can have 2 possible, either form the sigma bond or form pi bond. And the sigma and pi, they both could have the bonding and anti-bonding too. So this we learn, molecular orbital energy level diagram for lithium molecules, and with lithium we have the 1s and s. 1s form the 1s molecular orbital, and we have 2s, right? Sometimes we only talk about the valence electrons. We can, in order to save the space, we overlook this part, because this part, 2 electrons, and 4 electrons filled in here. This part did not really interferes what we're talking about here. Yeah, this part did not influence what we talk about here. Yeah. Anyway, all electrons are filled in, and so this is why for this one, for second period for diatomic molecules, I skip that part, but they still exist. Okay, I mean the 1s and 1s form the 1s sigma bond and 1s anti-sigma bond. They are located here, below here, but in order to save space, temporarily I skip that step. Okay, so we focus on the upper part, the valence electron part. So for these atoms, for example, the boron, carbon, and nitrogen, and for p orbital, they have 3 p orbitals, and px, py, and pz for this atom. The other atoms also have this one. So like we said, they can form either the pi molecular orbital by the p orbital. They also can form the sigma molecular bond, like here. They can either form the pi molecular bonding or they can form the sigma molecular bonding, by p orbital. So this is a diagram. So shows the pi molecular orbital have the lowest energy, and then the second lowest energy is sigma. They are both bonding molecular orbital. You see the energy of these orbitals are all lower than the atomic orbital. Before form that is all lower. But the anti-bonding, like the pi anti-bonding orbitals, the energy is higher, and so the sigma anti-bonding formed by 2px also has a higher energy. For this class, I don't not ask you to memorize this sequence of the energy level. But when you take the inorganic chemistry, perhaps you have to memorize that. But in this class, at least, I will give you this diagram in the test. Okay, before I go further, we introduce a few concepts. One's bond order. Do you remember we learned this one? We told you, and the bond order is equal to the number of bonds between two atoms. For example, if you have one bond between two atoms, the bond order is equal to 1. If we have two bonds, the bond order is equal to 2. If you have 3 bonds between two atoms, the bond order is equal to 3, like a nitrogen. We give you some example, right? So now let's take a look at the bond order from a molecular point of view. From the molecular orbital theory point of view. So the bond order is equal to the half of the number of electrons in the bonding molecular orbital minus the number of electrons in the anti-bonding molecular orbital. Okay, we will let you know how to do this calculation, but now you simply memorize that. So the second two terms is diamagnetic and paramagnetic. This is also not new. We introduced this one to you, but we didn't before we talk about the molecular orbital. That means all electrons are paired, and so this substance is not attracted by a magnet. So this is called a diamagnetic. We learned this one before. And on the contrary, so if there are one or more unpaired electrons exist, that substance is called a paramagnetic. That kind of substance can be attracted by a magnet. So I will show you some experiments here.
When liquid nitrogen is poured onto a magnet, the magnetic field does not affect the liquid. When we pour liquid oxygen onto a magnet, however, it is held by the magnet because oxygen molecules are paramagnetic. Paramagnetic substances have unpaired electrons.
You see, oxygen can be attracted by the magnet oxygen because they are paramagnetic substance. But nitrogen are diamagnetic. They are not intact with the magnet, so they directly falling down. But oxygen stay here, attracted. Okay, the last pair of the term is HOMO and LUMO. They are very important. You will frequently to see this HOMO and LUMO when you read the literature or you do research in the field of chemistry. So HOMO means the highest occupied molecular orbital. So you see highlighted by yellow, highest occupied molecular orbital is HOMO. HOMO is the highest energy that contain more electrons. In other words, HOMO is the molecular orbital of the highest energy that contain electrons. So LUMO is the lowest unoccupied molecular orbital. So that is the LUMO is the molecular orbital of the lowest energy that contains no electrons. Okay, we will talk about that later. Use some example. So this is a molecular orbital diagram for period 2 diatomic molecules. Again, to make it simple, we skip the sigma 1s and sigma 1s antibonding hold for inner shell electrons below here. Okay, we skip it now. We focus on the valence electrons only here. So let's see. Take a look at first the carbon. Carbon. When we talk about the valence electron, each carbon has 6 valence electrons, right? Because carbon belong to the groups. Sorry, have 4, yeah. Because carbon belong to the group 4, right? Altogether, carbon has 6 electrons, but carbon only has 4 valence electrons belong to group 4. So that means 2 carbon will have 8 valence electrons. And then we fill according to the rules, we fill the electron into the molecular orbital according to the energy sequence. This is the lowest energy. This energy increase here. So I fill 1 electron there, and 1 more electron here. You see, I continue filling in electrons to the orbitals. Altogether have 8. So I filled now 5, 6. This is the rules we talk about. If you have 2 electrons, you should put into the 2 different orbital, not put 2 into here and leave this empty. That against the Hond rule. So we continue and then we add 1 electron. Only after each orbital get 1 electron already, you can put electron there. And this is a molecular orbital for carbon. So the bond order, according to the definition, is equal to the number of electrons on the bonding orbital. Let's see which bonding orbital. This is the bonding orbital, right? Without star. Bonding orbital, you get 2. This is the bonding orbital without star. Without star, you get 4. 4 plus 2 is 6. So the number of electrons on the bonding molecular orbital is 6 minus the number of electrons on the anti-bonding. So this star indicates anti-bonding. So you have 2 on the anti-bonding. 6 minus 2 divided by 2. So the bond order is equals to 2. Yeah. Just in case you may forget, here, the bond order is equal to the half number of electrons in the bonding orbital and then minus the number of electrons in the antibonding. Okay, this is why we calculate that way. So the bond order calculated is equal to 2. So do we have the unpaired electron? No, because this is paired. 2 paired. Every orbital you see is paired. There's no unpaired electrons, so this is called diamagnetic. So the carbon is diamagnetic. Okay, then let's take a look at what is HOMO and LUMO in this case. So according to the definition, so the HOMO mean, okay, let's focus on HOMO first. The highest occupied molecular orbital. So which orbitals are occupied? We can say this is occupied, this is occupied, this is occupied. So these orbitals are occupied. So which one has which one's highest occupied? This one's highest, right? Yeah, the energy is highest among these 3 occupied molecular orbital. This guy has the highest energy. This is why this is a HOMO. Yeah, this is a HOMO. And for LUMO means lowest unoccupied molecular orbital. So these all all these orbitals are unoccupied, right? Unoccupied means no electrons occupied there. Yeah, unoccupied. And among that orbitals, which one has the lowest energy? Of course, this one. This one energy is higher than this. This energy higher than this. This orbital has the lowest energy among the unoccupied orbitals. This is why this is LUMO. Yeah. This energy is lowest. Of course, this energy is higher than this one, but now we are talking about the among the unoccupied, only this one. We do not compare this one with others occupied. If you compare this one with other occupied, of course, this energy is higher than all these. But this one, when you compare with unoccupied, so this is the lowest energy. This is called a LUMO, lowest unoccupied molecular orbital. I hope I make this one clear. Yeah. So, okay, this is the whole picture for that one. Before, as I said, I skipped this part. I skipped that part, but now I show all of them for carbon. Yeah, for carbon too. Yeah, this is the whole picture. Before this one, we already talked about when we only focus on valence electron only, we have this picture. But if we consider the total electrons, for total electrons, that is a whole picture. Yeah. I mean, it depends if you take some test exam. Yeah, depends. If they ask you what is the total number of electrons for carbon, you have to answer it's 12. Because one carbon has 6 electrons, we know it. If they ask you what is the total number of valence electrons, that will be 8. But that will not change the molecular orbital. If you focus on the valence electrons, you will focus on this part. You just did not see it, but they exist. Yeah. And if you talk about the total electrons, then you have to fill the electrons start from here. Because you talk about total, you should work on the inner shell orbitals too. Yeah. You will end up with the same configuration of electrons here. Yeah. Since this energy sequence is already clear, so if people ask you to write the electron configurations of the molecular orbitals, you can similar like writing the electron configuration for atoms. The only difference is this time the sequence is given. You don't have to memorize the energy sequence like 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. You don't have to memorize that sequence because the sequence can be found from here. The lowest, let me sigma 1s, sigma 1s antibond, and sigma 2s antibond is like that. You simply copy that one, sigma 1s hold 2 electrons, sigma 1s antibond hold 2 electrons, sigma 2s bonding hold 2 electrons, sigma 2s antibond hold 2 electrons. Okay, just like that, yeah. Just write down, copy what you have, you know. As I said, I will not ask you to memorize that sequence. Yeah, if you could, of course, it's great. But if you cannot, doesn't matter for this Gen Chem. Yeah, you will learn this one more from inorganic chemistry. I think we finished all chapter 10. Okay, let's stop here. Stop.